If you are packing for a hike, the physical limits of your equipment dictate every decision. Let's assume your backpack has a strict maximum capacity of 15 pounds. You have 3 specific items you can carry. There is a high-value survival tent weighing 10 pounds, a medium-value stove at 5 pounds, and a heavy, low-value camera at 8 pounds. To stay under the weight limit while maximizing the utility of your gear, you have to find the best combination. You also operate under a hard rule. You cannot bring half a tent or a fraction of a stove. You must either pack an item completely or leave it behind entirely. Maximizing total value under a hard capacity limit without using fractions is an optimization problem known as the 0-1 knapsack. The most straightforward way to solve this is using recursion. You write a function that calculates the total value of every possible combination of packing and leaving items. But because you face a binary choice, include or exclude, for every single item, you create a branching decision tree that grows exponentially. This exponential time complexity causes the recursive approach to fail on real-world datasets. To process larger lists of items, the solution requires dynamic programming. Dynamic programming relies on tabulation. Instead of calculating the same combinations multiple times in a recursive tree, the computer saves the results in a table for future reference. To decide if an item belongs in the pack, we evaluate 2 numbers. We compare the total value if we exclude the current item to the value of including it, plus the best possible value for the remaining weight capacity. By executing this logic across all items, we build a 2D matrix, mapping every item on the y-axis against every possible capacity on the x-axis. This grid resolves the time delay, dropping our complexity to O of n times w. However, maintaining a 2D matrix stores thousands of historical states we no longer need, consuming excessive memory. To calculate the answers for our current row, the algorithm only ever pulls data from the single row directly above it. Because we only need the previous row's data, we collapse the matrix into a one-dimensional array. This flattened matrix introduces a traversal trap. If the array updates itself from left to right, we overwrite the data we were planning to use for future calculations. Moving left to right means that when the formula evaluates larger capacities on the right, it references smaller capacities on the left that have already been updated with the current item. The algorithm would then accidentally pack the same item multiple times. To fix this, we traverse the array in reverse. By moving from right to left, the pointer references data from the previous state that hasn't been changed yet. Reversing the loop direction is the mechanic it allows for space optimization while maintaining the 0-1 constraint. To visualize how this works, imagine an array filled with zeros and a 4. If you use a new item with a weight of 2 and a value of 5, you can see how calculating from right to left preserves original values until they are no longer needed. In Python, we initialize a 1D array of size w+1 with zeros. An outer loop iterates through items. An inner loop counts backwards from capacity w. Each cell updates to the maximum of its current value versus including the new item. This structure allows the algorithm to handle both time and memory as efficiently as possible. The optimized solution combines comparing exclude and include values, compressing the matrix into a 1D array, and the reverse traversal. Solving these problems relies on visualizing how data overwrites itself in memory. When you can see the data moving, the code becomes an extension of that logic.